Hello everybody! Topic of my research is image compression techniques comparison, singular value decomposition and discrete cosine transform. What I would like to cover at this presentation is first compression, what is it and what is the use for, in particular in images, methods overview, singular value decomposition and discrete cosine transform, performance criteria, which measures we can use to actually understand how we compress the image. We would go with a demo to look at this method, so to say, live, which we will see which parameters we can tune, and we will discuss the results. The process of reducing the size of a data is often referred as a data compression. Compression is useful because we reduce the resources required to store and transmit actually the data. And shortage of the data is necessary nowadays as we have big amounts of data. In particular in images. When you look at any color on your screen, you're actually looking at the mixture of red, green, blue colors displayed by small pixels on your screen. They're displayed on your screen as grid. So it means if you have, for example, grayscale image, you would have to store, and it's 1K by 1K, you'd have to store 1 million pixel values. And if this image would be colored, it would be triple of this number. It would be 3 millions. This equals 1 megabyte for a grayscale image and 3 megabytes for a color. Storing image in a large database is a problem that image compression really can solve by reducing the size without really degrading the image quality. The image compression also allows overcoming the data transmission problem by reducing compression can be either lossy or lossless. Lossless compression reduces bits by identifying and eliminating statistical redundancy. No information is lost in lossless compression. Lossy compression reduces bits by removing unnecessary or less important information. And the first technique that we will review is discrete cosine transform. It's lossy. The most popular technique for image compression over the past several years was DCT. Its selection as a standard for JPEG is one of the major reasons for its popularity. DCT is used for signal processing, image processing, for data compression. DCT is used to map an image space into a frequency, and it has many advantages. One of them is that it has the ability to pack energy in the lower frequencies for image data. Before we will start with how does image are compressed using DCT, I want to know you how does it works. For those of you who are not familiar with cosine function, it's quick reminder. Cosine function looks like this. And the first wave has standard frequency and the second one has higher frequency. As we add them together, it's weighted sum, we can get another wave, and it will be like combination of two, and it has more complex shape than previous two. As we increase the number of such base waves, we increase the variety of waves that can be produced from them. We can also tune weights. For example, here, like we get in just half of the first one and half of the second, and that's it. And we can tune these weights to be like any numbers. The way discrete cosine transform works is we're just taking some data and we're trying to represent it as a sum of many waves like this. And we think that we can get rid of high frequency components and the general content of signal, for example, picture, will be still there. This is just one-dimensional DCT with two components. The secret how it works mathematically is if we have a signal of 8 ln, then we can find that we can represent it using 8 cosine waves of different frequencies. The same is true for the image. Let's imagine image, or I don't know, the blob of the image 8 by 8 pixel group, and each group is encoded with its own DCT. Each group of these 8 by 8 pixels can be represented as sum of 64 cosine waves. The left corner is essentially flat, and in this direction and in this direction, for x and y, we increase the frequency. As we increase the frequency in both directions, we can get check table pattern. This is a high frequency information we are encoding at these regions. So this is basically 64 cosine function that can be combined to encode any 8 by 8 image. So we do combination of all of this weighted by some coefficient, and it's a number representing contribution of each component, this component, this, for a whole image. And what we basically do in DCT, we are calculating this coefficient. Let me show you an example of 8 by 8 image. To start, we will need to center all of these values. They are currently centered between 128. And we center these values around 0, because cosine is from -1 to 1, not from 0 to 1. So now we can use DCT to calculate contribution of each of our cosine wave added together, and they will create this matrix. So this is our cosine waves, and they are all contributing in this image. And we are calculating this impact coefficient matrix that represents a number that each wave contributed to this image. And basically we'll come up to this matrix. And as you remember, this is the low frequency components, and this is the high frequency components. And as you can see by numbers, the low frequency components contributed and so to say have much bigger effect on input image. For example, this one is -0.04, and compared to these numbers, it's like really small. So if you took these coefficients away, the image would be pretty much identical. That's what we're doing. We can have quantization matrix to divide these numbers by some number and obtain zeros, or we can just reduce by some number these small numbers. And the next one would be singular value decomposition. Value decomposition is very interesting way to break up the matrices. And what is SVD is we split matrix A into the three components. Matrix A has dimension m by n, and matrices U and V transpose are orthogonal matrices that has dimensions m by m and n by n, and they consist of singular vectors, left singular vectors and right. And sigma is diagonal. It consists of singular values in the diagonal and other components is zeros. So abstracting this matrix A into the components, we can see that matrix multiplication yields to the m by n original size of matrix A. And how SVD can be used in image compression, and it's really used. So let's understand why and how. The reason why SVD is computed is because you can use first components of these matrices, I mean matrices U, sigma and V transpose, to give you a close approximation of what actual matrix looked like, matrix A. Going back to our size example, for example, we decided to take first component, just one. And we can see that by dimensions of these matrices, that we can reconstruct m by n matrix. And the most important, so to say, information of this matrices is stored in the first component. So we hope that we won't lose too much data after this reconstruction. That's like a great theory, but when you compute these matrices using your models of precision, or I don't know, random K or R, what does this image actually look like? We will see in the demo, but before the demo, I want to discuss performance criteria in image compression. I decided to use three of them: compression ratio, mean square error, and peak signal to noise ratio. The formulas is given, but the compression ratio is the ratio between the original image size and compressed image size. Mean square error is just pixel-wise error between, and it's a measure of distortion rate in the reconstructed image. And peak signal to noise ratio is just, I would say, reversed mean square error, but there is square root of it and multiply and logarithm, so it's not that easy. But still, when we are getting mean square error, we're just getting the smaller values as reconstructed image and original image is closer, and the peak signal to noise ratio is just reversed in these terms. So now let's go for the demo and see what we obtained. So now we can start with the demo. Here we can see the interactive notebook, and we can change the images. You will look at the code at the implementation later, but what is interesting that you can play with the images or with another stuff, and for example, it's for SVD is we are getting the number of k, as I discussed previously, the number of components that we will take to reconstruct the image from 0 to the size of the image, and we can get mean square error and the peak signal to noise ratio, and obtain compression ratio too. So you can look at the images visually. If we will take from which k we will start not to recognize the image, for example, and sorry for that, it's just re-rendering every time, every step, our image. So you can play with even less k, for example, from which, okay, yep, so you can see from which k you can recognize the cat, and see mean square error and peaks to signal noise ratio. Okay, so for DCT it's the same. Implementation is definitely different, but you can play with k and see mean square error, peak to signal noise ratio, and compression ratio. Okay, so k here is from 0 to 8. Why it's such? As I explained, when we have the matrix of coefficients of these cosine waves, we want to decide which values we will reduce. And here I have two implementation, for example, filter by threshold and filter by number. I use now filter by number, so it's basically number from 0 to 8, which values from this matrix will be reduced. But then again, as a JPEG implementation is, you can add here like quantization matrix and do stuff that they do in JPEG. So you can look at the measures and yep, play with the pictures and the parameters. Image compression is used pretty much in every system which is used for image storage, sending, or processing. What we've come up to that the both algorithms are loosey. They are both usually used as sub-algorithms. We can tune degree of compression by varying some value of k, for example, as I do in DCT and SVD. And what is interesting that to obtain the similar mean square error, DCT works much faster, and usually it's all about frequency-based models and other ones. For example, like SVD do with just calculating singular vectors and singular values. So that's it. Thank you for your attention.